There are four variables that are going to affect the amount of radiation that one is exposed to. The first of these, of course, is the activity of the source. The strength of the source is probably the single most important factor. The second of these would be the amount of time that one happens to be exposed to that particular source. The third of these would be the distance that one is from the source. And the fourth one would be the amount of shielding, if any, between you and the source. So there is an equation, two equations on pages 208 and 209 of your textbook, equations 12.3 and 12.4, and the first of these gives a relationship for three of the four factors that I talked about. And this is x equals gamma a t divided by d squared. X is the exposure, and this is in Roentgens. A is the activity in millicuries. T is time, and that's in hours usually. And D is distance in centimeters. And since this is an inverse square law relationship, that's going to be centimeters squared. Okay. Gamma is actually the exposure rate constant, and that is going to have the units. If we're using the units that I just specified, gamma will have the units of Roentgen centimeters per millicurie hour. Roentgen centimeters squared, I'm sorry, per millicurie hour. So that would be the units for gamma. And that, as I said before, is the exposure rate constant. Okay, and there is a problem in your book that specifies someone sitting 1.5 meters from a 25 millicurie cesium-137 source for 40 hours every week. And we want to know what the exposure is on a weekly basis. So we can just substitute in the values that we have. The rate constant for cesium-137, and that rate, the rate constant gamma will depend on specifically which radioisotope that we're dealing with. But for cesium-137, it's the value is 3.27 Roentgens, 3.27 Roentgen centimeters squared per millicurie hour. So this problem would then become x is going to be equal to 3.27 Roentgen centimeters squared per millicurie hour times 25 millicuries times 40 hours. This is a 40-hour week, divided by the distance, and the distance was given as 1.5 meters, but that becomes 150 centimeters. 150 centimeters, because we want all these units to be the same. So it's 150 squared centimeters squared. Centimeters squared is going to cancel out. Curies will cancel out. Hours will cancel out, and we're left with an answer in Roentgens, and it's going to come out to 0.145 Roentgens. After you've done the math, it's 145 milli-Roentgens. So the question then is, supposing we want to actually reduce this, well, we could move, maybe we can't move the individual further away because maybe that particular station where she works, that's where the equipment is and nothing can be moved around. So we could look at, for instance, at other ways in which we might be able to lessen that exposure. If she has to be there for that amount of time, we can't do anything about the time, but we could do something about shielding. So that was something we haven't said anything about. Now, we had, way back in Chapter 5, we had an expression that actually gave us, we had something called a linear attenuation coefficient, which you might remember, which is abbreviated with the symbol mu. And we had an equation that said that the natural log of I divided by I0 was equal to minus mu times x. So this is the linear attenuation coefficient. These are, you could think of these as intensities. This is the intensity of the radiation at the source. This is the intensity after whatever is actually come out of the shielding. This is what we're actually seeing out of the shielding. So this gives us something called a transmission factor. And the natural log of this relationship gave us minus the attenuation coefficient times x, which is actually the thickness of the shielding. So we can actually express this in another way. We can invert these two things, which is what we did in this chapter. If we put I0 over I instead of having I over I0 as we did in chapter 5, we can say that the ln of I0 over I is actually equal to mu x. We get rid of the negative. Once we flip this over, we get rid of the negative sign, and then we can, and this is shown on page 209, and then we can actually substitute in our I0 and I values. So this was 145, that's what we calculated, 145 milliroentgens, and we want to bring this down to 2 milliroentgens. So we're going to go from 145 to divided by 2 milliroentgens, and that's going to be equal to mu divided by x. The value for mu is 1.07 reciprocal centimeters. So I want to 1.07 centimeter minus 1. And when we do the math here, we're going to get a value of x, which will be 4.0 centimeters. So that is actually the amount of shielding that we would need to cut the amount of exposure that this person, if we had 4 centimeters of lead, we could cut the exposure from 145 milliroentgens per week down to 2 milliroentgens per week. Quite a bit of savings. If we wanted to calculate this in terms of half value layers or 10th value layers, we could do that very easily. A half value layer is the natural log of 2 divided by mu. That would be ln of 2 divided by 1.07 reciprocal centimeters, and that gives us a value of 0.65 centimeters. And similarly, we could do it the natural log of 10 divided by the natural log of 10 divided by mu would be ln of 10 divided by 1.07 centimeters. That gives us 2.2 centimeters. So we could use that then to find out that would be equal to 1.8 10th value layers, or in the previous example, 4.0 centimeters divided by the 0.65 half value layer gave us 6.2 half value layers. So that we can use this equation to determine all of those kinds of things. But what I wanted to mention was that we can actually put in a value here. We can modify this equation by putting in the value b. We multiply this by b, which actually is the shielding, the transmission factor. So the transmission factor really is nothing more than the ratio of I to I0. So if we know I and we know I0, we can substitute this in for b, and that gives us really the complete equation. And this equation right here really describes everything that you would need to consider if you're trying to find out what exposure rate you actually have in a given situation. So that's really all the math that we have in this particular chapter, and that will kind of conclude what I have to say here in terms of radiation protection, except for one other thing that I wanted to mention, dealing with bremsstrahlung, or bremsstrahlung production. So when we're talking about shielding, I mentioned before that it's nice to have a lot of shielding, because you could see that that the more shielding you have, the more you're going to actually reduce the amount of radioactivity that you're going to be exposed to. And this is particularly good if you've got X-rays. You'd like to have a nice thick shielding to protect you from X-rays. But when you're dealing with things like beta radiation, you have to be very, very careful, because beta radiation, if you have too much shielding, and particularly if you're using materials that have high Z values, the higher the Z value, the more likely it is that your X-rays are actually going to be, rather your beta radiation is actually going to be involved in bremsstrahlung production. So you know that the higher the Z value, the more likely it is that a gamma electron, a beta electron will produce X radiation when it approaches a high Z nucleus. So using lead, for instance, which has a high Z number, 82, that would not be very, very desirable if we're trying to shield against beta radiation, because we'll be making, if we do that, we're going to be making more bremsstrahlung, and then we're going to have X-rays, and that's just going to require more lead. So for instance, I think I showed you in a previous video a little device that I have that is called a tracer, and the tracer is nothing more than a little cylinder that's coated with something like zinc sulfide on the inside, and there's a little capsule in here that contains tritium. And the tritium beta radiation is actually striking this zinc sulfide screen here, and it causes this entire tube to light up. I've got one that's blue and another one that's green. Just depends on the amount, on the type of phosphor that you actually have on the tube. But these things are always coated in plastic. Well, part of the reason, of course, is you want them to be transparent. But you could have coated them, for instance, in something like a high lead glass. I mean, there's a form of glass which is also transparent that contains a lot of lead. And you really wouldn't want to do that, because then you would be producing a lot of bremsstrahlung, and then you'd have to use a lot more lead to protect yourself. So by putting this in plastic, there's very, very little if any bremsstrahlung. I've never been able to actually detect at the surface of this device. I've never been able to detect any radioactivity. But in fact, if there were any, we could then surround this in lead. And if we put lead around here, then any X radiation that might actually be produced from the bremsstrahlung would probably not get through the lead. But actually surrounding this in lead without the plastic first, that would be dangerous, because then we would be producing more bremsstrahlung. Okay, so that's really all I have to say about the subject of radiation protection, and next week's lecture will concern itself with X-ray production. Once again, thank you very much for your attention, and I wish everybody good luck.